Hi, I'm Jessica, and we're here at Speculas Building Innovations in Pharr, Texas, owned and operated by Gene Fairstead since 2000. Let's take a look inside and see how things operate. They specialize in distributing building materials throughout the Rio Grande Valley, and one of their main products is Drive-It. Drive-It is an exterior cladding system used in commercial and residential construction. This facility, Speculas has 3 other distribution locations throughout the Rio Grande Valley, and one of their main problems in transporting the product is minimizing transportation costs, which will yield private solutions to help them. The key problem managers face is how to allocate resources among various activities or projects. Linear programming is a planning process that allocates resources such as labor, materials, machines, and capital in the best possible way so that costs are minimized or profits are maximized. And in this case, Speculas is faced with a transportation problem, and our purpose is to minimize the cost of shipping goods from one location to another so that the needs of each arrival area are met and every shipping location operates within its capacity. Speculas has 2 locations in town. The office receives orders from 2 customers and each requiring Drive-It. Customer A needs 50 buckets of Drive-It while customer B needs 70 buckets of Drive-It. And then there's 2 warehouses on the east side and on the west side of town. The warehouse on the east side of town has 80 buckets in stock. The west side warehouse has 45 buckets in stock. Delivery costs per sheet are as follows: 50 cents from the eastern warehouse to customer A, 60 cents from the eastern warehouse to customer B, 40 cents from the western warehouse to customer A, and 55 cents from the western warehouse to customer B.
There are 4 things to consider: east warehouse to customer A, east warehouse to customer B, west warehouse to customer A, and west warehouse to customer B. The variables need to stand for the number of buckets being shipped. There are 4 different sets of Drive-It buckets shipped from east warehouse to customer A, which is AE, shipped from west warehouse to customer A, which is AW, shipped from east warehouse to customer B, which is BE, and shipped from west warehouse to customer B, which is BW. Customer A wants 50 Drive-It buckets and customer B wants 70 Drive-It buckets. The equation is as follows: AE plus AW equals 50. So AW would equal 50 minus AE. The second equation would be customer BE plus customer B West, which is 70. So BW would equal 70 minus BE. Since the warehouse can ship no more than 80 buckets and the western warehouse can ship no more than 45 buckets, then the following formula is as follows: 0 is less than or equal to AE plus BE is less than or equal to 80, and 0 is less than or equal to AW plus BW is less than or equal to 45. The optimal cost equation will be as follows. The cost equals 0.5A east plus 0.6 B east plus 0.4A west plus 0.55 BW. The equations labeled earlier as equation 1 and equation 2 will allow us to substitute and get rid of the two of the variables in the second inequality. So the formula will be as follows. 0 is less than or equal to AE plus BE is less than or equal to 80, and 0 is less than or equal to 50 minus AE plus 70 minus BE less than or equal to 45. Simplifying the second inequality would give us the following formula. 0 equals less than or equal to AE plus BE less than or equal to 80, and 0 less than or equal to 120 minus AE minus BE is less than or equal to 45. Multiplying through by -1 and adding 120 to all three sides of the second inequality, you get the following formula. 0 is less than or equal to AE plus BE is less than or equal to 80. 120 is greater than or equal to AE plus BE is greater than or equal to 75. Since AE plus BE is no less than 75 and is no more than 80, then these two inequalities reduce to 1. The formula is as follows. 75 is less than or equal to AE plus BE is less than or equal to 80. You can also simplify the optimization equation. Cost would equal to 0.5 AE plus 0.6 BE plus 0.4 AW plus 0.55 BW, which gives you 0.5 AE plus 0.6 BE plus 0.4 times 50 minus AE plus 55 multiplied by 70 minus BE. That in turn gives you 0.1 AE plus 0.05 BE plus 5850. Due to the size of the orders, you have the following. 0 is less than or equal to AE is less than or equal to 50, and 0 is less than or equal to BE is less than or equal to 70. Since there are only two variables now, we'll be graphing with the following, x and y. We'll rename the variables x equals AE and y for BE. Then the entire system is shown as follows. To minimize cost, you would have 0.1x plus 0.05y plus 58.50, and these would be subject to the following. X is greater than or equal to 0, x is less than or equal to 50, y is greater than or equal to 0, and y is less than or equal to 70. Y is greater than or equal to negative x plus 75, and y is less than or equal to negative x plus 80. Looking at the graph, you will notice that the shaded area represents the feasibility region at y equals negative x plus 75. After the corners were tested at 5 and 70, 10 and 70, 50 and 30, and 50 and 25, we got the following minimum cost when we shipped as follows. 5 buckets from East Warehouse to customer A, 70 buckets from East Warehouse to customer B, 45 buckets from West Warehouse to customer A, and 0 buckets from the West Warehouse to customer B.